Good afternoon, everyone. Welcome to our State of the Climate webinar. For those joining us for the first time, welcome. And for anyone who joined us for our webinars before, welcome back. Today we'll be giving you an in-depth look at the most recent State of the Climate report released in late 2018 by the Bureau of Meteorology and CSIRO. My name is Angela and I'm delighted to be your moderator today. Claire is our producer and will help moderate your questions. Hi, Claire.
Hi, Ange.
Please send them through via the chat function and we will address as many as we can during the webinar. But before we begin, may I ask for your attention as we cover off some housekeeping items. Our broadcast today will run for 60 minutes with plenty of time allocated for questions. This webinar is also being recorded and the video will be shared with you via email. For first-time webinar attendees, please see some helpful tips on your screen. Please note the chat box where you can send through any questions or feedback for the presenter. Please use this and not the Q&A box to send your questions to us during the session. And as I mentioned before, we'll answer as many as we can during the allotted breaks. We do have a very high volume of listeners today, ladies and gentlemen, and so we do apologise if we cannot address all questions during the webinar. If the chat box is not visible on the right-hand side, please open it using the chat icon within your control panel. And at last, I am delighted to introduce you to our experts and lead authors of the report, Dr. Michael Gross and Dr. Lynette Betio. Welcome, Michael, and welcome, Lynette. Dr. Michael Gross is a there you go. Good to have you. Dr. Michael Gross is a research scientist at the CSIRO Climate Science Centre in Hobart. His research focuses on the science of climate change processes, understanding climate change as we've seen to date, and how we can produce future climate projections that are useful for a range of stakeholders. He previously worked in marine and Antarctic science and is the author of numerous research papers, book chapters, and stakeholder communication products. Dr. Lynette Betio is a senior climatologist in the climate monitoring team at the Bureau of Meteorology. She has a PhD in climate science. The Climate Monitoring section is responsible for the preparation and analysis of Australia's instrumental climate record. Lynette examines and communicates on changes to Australia's climate, including long-term trends in rainfall and temperature, and the interaction with extreme events. Another focus is drought across Australia and how the Bureau can best communicate and inform around this. Welcome all. Lynette and Michael, great to have you with us. Who would like to tell us a little bit more about what we'll be covering today?
Thanks, Angela, and yeah, very happy to be here. So I'll start off today and just looking at our key messages from the report. So as you said, our latest report was released in late 2018. It's released every 2 years, and this is the 5th report in this series. And really drawing on that latest climate science, the latest research, the latest data to describe those changes and long-term trends in Australia's climate. So really important, those trends that we're seeing in previous reports, they're continuing in this report. So Australia's climate has warmed by just over 1 degree since national records began in 1910, and this is leading to an increase in the frequency of extreme heat events. There's also been a long-term increase in extreme fire weather and fire season length across large parts of Australia since the 1950s. Michael?
Thanks very much, Lynette. So later in the session, I'll be covering some content on oceans, greenhouse gases and future climate. And similar to the previous sections, some of these key messages are basically a continuation of things we've seen before. So oceans around Australia have warmed, and again, this is by about 1 degree, and this is contributing to longer and more frequent marine heat waves in several regions around Australia. Also, sea level has continued rising. The absorption of carbon dioxide from the atmosphere into the ocean is changing the pH of the oceans. Global carbon dioxide in the atmosphere has increased to levels not seen in at least 800,000 years and likely in the last 2 million years or more. Australia is experiencing climate change, and some of those changes can be attributed to human activity right now, and many impacts are being felt by communities and in industry sectors. And this report draws on the best available peer-reviewed information from within CSIRO, the Bureau, other Australian scientific organisations and around the world, and presents multiple evidence sources. Going to the next slide. To give our webinar, we'll start with content on temperature, rainfall, fire weather, and compound extreme events. These are on the kind of land and atmosphere side of things. I'll then give an overview of greenhouse gases in the longer context and also what we measure here in Australia, then go on to talk about what's happening in the oceans and what we can expect from future climate.
So I'll start off and just starting with this slide here. So it's actually when we released the report, this is a retweet of a tweet that we put out from AFAC, and AFAC is the National Council for Fire and Emergency Services in Australia and New Zealand. So talking about how the report, it's not just a report released on the day, but that information is used to help inform our partners in fire and emergency services, in this case, and government and organisations around Australia. So over 100 years of data, climate data, included in the Bureau's climate record, just really helping to inform decision making around the challenges of climate change and increasing extremes. So Michael's going to talk more about greenhouse gas concentration later on in this webinar, but I just wanted to start here because it's really the increases in atmospheric gases such as carbon dioxide that's really driving these changes. So as we can see from this graph earlier on, it goes up and down. It's a fairly regular cycle, and in the last 200 years or so, we've seen that rapid increase in carbon dioxide in the atmosphere. So what changes have we seen in response to that? So these changes that we've seen include changes in temperature. So we have here sea surface temperature in the oceans around Australia and Australian surface air temperature. And looking at this graph, we can see that it goes up and down a lot, but we can also see a steady rise. So Australian climate is quite variable. We see variations in our temperature in response to climate drivers such as El Nino and La Nina. So we see the up and down. But in more recent years, we've seen that on top of a warming trend. So the warming trend being the climate change part of that story, and the up and down being that variability. And what we're seeing over the land in Australia is also reflected in the warming that we're seeing in the oceans around Australia. So we've seen, I'll just go back, so we've seen around a 1 degree warming in temperature, and so 1 degree, it doesn't sound like a large number when you say 1 degree, so I just really wanted to talk to why does that 1 degree matter, and we talked about that 1 degree warming in the introduction leading to an increase in heat extremes. So I just wanted to look at this slide. This is one of my favourite figures for really explaining why that 1 degree matters. So if you look at the curve, so if you think around that zero where you see that peak of the curve, so this is describing how it changes from the average. If you think most of the information, describing temperatures, if we line all our temperatures up from cool to very warm, so most of the temperatures are around average, and we have some very cool temperatures and we have some very warm temperatures. I like to, if I'm giving this to a room, well, we can imagine our virtual audience, and if we lined our virtual audience up, and we'd have some shorter people, and we'd have some taller people. I like to think I'm pretty average height, and I'd probably be in the middle with most people around that average. So that curve that's further to the left-hand side there, that's the 1951 to 1980 curve. So we can see that those curves have shifted a little bit further to the right. So that's just with that 1 degree of warming, that 1 degree shift. So if you're looking on the right-hand side there, you can see around that that standardised anomaly, that number 2 there. So very warm events that only happened 2% of the time, or 1.97% of the time, for the period 1951 to 1980, are now happening 12.48% of the time. So a real shift in the frequency of those very warm events that we're experiencing. So just that 1 degree shift in the average, in the mean, has really impacted on how often we're seeing those really warm events. And those really warm events are often where we see the most impact from climate change. So you don't really feel a 1 degree change or that mean change in temperature, but you really feel that impact of heat waves and those very warm months. And likewise with daily temperature, this is another way to show how these extreme heat events are increasing. So with those, what we're seeing here is those daily means, so average over all of Australia, and we're seeing that top 1% of those days compared to the month that it was recorded in. So looking at 2013, which is near the right-hand side there, which is that sort of that highest one, over 28 those very warm extreme days in 2013. So we can see towards the right of the graph, there's been that real increase in frequency as we go through time. Whereas at the start of last century, with records starting in 1910, there wasn't as many days with those extreme temperatures compared to what we're seeing now. So another area where our climate is changing, where we're seeing those changes, are changes in rainfall across Australia. So there's been that real shift. One of the major trends that we're seeing is that drying shift across southern parts of Australia. And this is especially evident in that April to October period. So an important agricultural period for southern Australia, and an important period too for our water resources as we get much of our rain during this part of the year. So what we're looking at here is a graph of 20-year April to October rainfall deciles. So taking those 20 years, those last 20 years, and looking at how those last 20 years compare to all the other 20-year periods that have gone before, with national records starting in 1900. So how do these most recent 20 years compare? So we can see that over large parts of southwestern Western Australia, we can see lowest on record. So this most recent period has been lowest on record, and that very much below average is that bottom 10%. So with the last 20 years for much of southeastern Australia and southern parts of Australia being in that bottom 10% of what we've seen compared to other periods. So again, with rainfall, so these graphs here are looking at the rainfall anomaly for southwest Western Australia for April to October, and the rainfall anomaly for southeast Australia for April to October on the right-hand side there. And so what we're seeing, you first look at this, and similar to temperature, there is large variability in the rainfall that we're seeing. So similar to temperature, this is against the 1961 to 1990 average. So we're looking at the anomalies around that average, and we look at anomalies to look at how it changes with respect to that mean. And what we can see with southwest Western Australia, there's large variability, but we can also see in the later part of the period, so going more towards the right there to we can see a decline in that rainfall received since around the 1970s. So since around the 1970s, for April to October, we've seen around a 20% decline in rainfall compared to the period before. And what we're seeing too, we're not seeing those really wet years as we saw earlier in the period. So likewise in Southeast Australia, you see a similar decline in rainfall starting around the 1990s. So this is really associated with a shift in those weather systems. So with Southwest Western Australia during April to October, getting a lot of its rainfall from those frontal systems coming through and not seeing as many frontal systems from that period coming through.
Can I ask a quick question, Lynn? We had a question from John. He said, when you say southeast of Australia, what area are you talking about? Does it include the Riverina of New South Wales?
It really includes that southern part of New South Wales, Victoria, and some parts of South Australia, eastern South Australia, and Tasmania. I can confirm that area and get back to you. It is in the report, so we can get back to you on that. But so southwestern Australia, that smaller pocket in WA, and southeastern Australia over a larger region, and seeing that decline from around the 1990s. So with southwestern Australia, mainly relying on that frontal rainfall for those anomalies of rainfall coming through. For that rainfall coming through, and seeing a real decline in that rainfall as those frontal systems are pushed further south. Now, southeastern Australia, we get, I say we because I'm living in Melbourne, but southeastern Australia gets its rainfall from a lot of other sources. So it's seen a decline in that rainfall from those frontal systems, but we get the tropical moisture coming through from the northwest cloud band, cut-off lows, which has also seen a decline. But there's other sources as well. So there hasn't been as a decline. It is more recent than what we see in southwestern Australia. Yes.
And Lynn, please, one more clarification from your temperature graph. David's asking us, in the first temperature graph shown today, what temperature represents the benchmark on the graph? That is the zero on the x-axis.
Yeah, sorry, I realised as I explained the anomalies in rainfall that I didn't explain that the anomalies in temperature were taken from the 1961 to 1990 mean as well. So we're looking at the anomalies in temperature there from compared to the 1961 to 1990 average.
So he's saying what temperature represents the benchmark on the graph, that is the zero?
So it's the zero is the 1961 to 1990 average.
Yeah. Thank you.
Thank you, David. Hopefully that's clarified things.
So what we're also seeing in rainfall, so we're also seeing across October to April in the rainfall, with that 20-year period compared to all other periods, we're also seeing more rainfall in northern parts of Australia, very much above average for the last 20 years. So we talked about fire weather in the introduction. So this is one area that's a very active area of study. So looking here at the Forest Fire Danger Index. So the Forest Fire Danger Index, it takes into considerations the maximum temperature, the temperatures that we're seeing, wind speed, the humidity, the state of the vegetation. So really, we're talking about the conditions that are conducive to fire. So what we've seen, that these fire conditions are worsening. So we're seeing an increase in the length of the fire season, and we're seeing more intense, so more frequent, intense fire conditions. So this is largely seen across, we can see on this graph here again, across parts of southeastern Australia, we're seeing an increase in those fire weather conditions. So those conditions that are conducive to bushfire weather.
So Rob just quickly asked us, large parts of South Australia are considered forest. Does the summary of FFDI also equate to grassland risk?
Again, it does take into it does take into account some consideration of the vegetation, but this is, again, it's done on a national scale, so we're using that single measure.
Thank you.
So one thing we looked at in the report is compound extreme events. So we've talked about the trends in single variables. So we talked about trends in rainfall, trends in temperature. And these can often be considered to, we see such as fire weather, that these can combine to produce those impactful and hazardous events. But compound extreme events, they can also be events that happen within simultaneously across a larger region, which may impact on your ability to respond to those events, or it can be in timescales, again, where you're stressing the system and you have to respond within a certain time. So one example that we referred to in the report was that what we saw in Tasmania during 2015 to 16. So those background warming trends and the background drying trends and that natural variability as well impact on top of that, seeing the extreme heat and low rainfall across Tasmania. And then we saw a transition to record atmospheric moisture and heavy rainfall in June in 2016. So just having a look at that and what that looks like on our maps, and these maps are available on the Bureau website as part of what we monitor. So Tasmania in October 2015, again with those rainfall deciles, the dark red on the left-hand side there being lowest on record for October, and the very much below average being that bottom 10%. So much of Tasmania being lowest on record for October. And again with the maximum temperature highest on record and in the top 10% for much of Tasmania for October 2015, and really setting up those preconditioning for those bushfires that occurred during the summer season. And then in June 2016, we saw record high rainfall. So on the right-hand side there, rainfall highest on record and very much above average across large parts of Tasmania, and this was associated with floods across Tasmania. And just drawing your attention there to the sea surface temperature anomaly that we saw in the Tasman. Again, this is monitored on the Bureau's website, and again, it's the anomalies with respect to a 1961 to 1990 average. So you can see that one that really sticks out there, that's May 2016. So really a large anomaly that we just hadn't seen before compared to the years before. So I will pass on to Michael then, and he will go through the rest of the presentation.
Thanks very much. So I'm going to go through, first of all, atmospheric composition and concentration of greenhouse gases, then on to oceans, and then finish on future climate. So taking another look at this plot and putting the recent greenhouse gas or concentration of carbon dioxide in a very much longer context, we can put the recent measurements, which are visible as a blue line right at the very far right of this graph, going back through time from the year 2000 through to the year 0. We can reconstruct what the CO2 concentration was by looking at things such as ice cores. This is the bubbles trapped in ice in Antarctica that make a natural record of what the carbon dioxide level was. And then jumping to the left panel, we very much stretch out the timescale to be hundreds of thousands of years before the present. So this is a very long ice core with a very long record going back much further. So just be very aware that those timescales are very different. And you can see in the much longer record, there was cycles of carbon dioxide increasing and decreasing through ice age cycles, reinforced by what we call climate feedbacks. But the concentration of carbon dioxide never really got above 300 parts per million and was averaging at about 280 parts per million as we came into the modern era. Then in the last 2,000 years, it was fairly steady at about 280 or less parts per million of carbon dioxide through to the recent time where it has been shooting up. And so just to put a little bit more context on those time frames and what they mean, just bringing up the first little annotation, Lynette. This is where our friends Homo neanderthalis kind of emerged, then Homo sapiens emerged, and then just in the last little sliver of that broad plot is where we saw permanent settlements and agriculture coming on for humans. So we know that carbon dioxide through all of this time was closely coupled to global temperature, and we expect that relationship to hold now and into the future. So this is work from Australian Antarctic Division together with CSIRO and other research organisations around Australia to reconstruct that carbon dioxide back through time from Antarctic ice cores, and then more recent measurements. So going to the next slide, here's the direct measurement of carbon dioxide concentrations measured at Cape Grim, which is in northwest Tasmania, which is one of 3 global clean air stations. There's a network of more than that, but these are the 3 most prominent and important sites. The other ones are in Hawaii and in Greenland. And here you can see, in a very much different timescale than the previous graph, since the mid-1970s, we've seen a fairly steady increase in carbon dioxide concentration in that clean air, that baseline air coming and hitting northwest Tasmania. You can see a slight wiggle in the seasonal cycle, but the trend is extremely clear. Going to the next graph. Here we can put together the measurements at Cape Grim and the other air monitoring stations and other lines of evidence and data to have a look back through the last 100 or so years since the year 1900 at the concentration of all the different greenhouse gases, so that's carbon dioxide, methane, nitrous oxide, and other greenhouse gases such as the halocarbons, and look at what effects they have on the atmosphere over that time frame. The left-hand graph shows the effect they're having in terms of radiation balance, which is what we really care about in terms of the climate. So this is expressed in watts per metre squared, which is the difference in radiation going in and out of the atmosphere. And you can see the effect has been steadily increasing. The effect of carbon dioxide is the largest, but the other ones are also very notable. And there's been an increase in 3.2 of those units, watts per metre squared of energy into the climate system compared to pre-industrial times, just from these long-lived greenhouse gases, we call them. The graph on the right shows the concentration in parts per million of carbon dioxide in the blue line. They're reaching that kind of symbolic threshold of 400 parts per million in 2017 and now steadily above that concentration. The red line is if we put all of the different greenhouse gases together and express them in the equivalent of carbon dioxide. If they were all carbon dioxide, what effect would they have? We call this CO2 equivalent. And in 2017, we can now officially declare that measurement reached the symbolic or the milestone of 500 parts per million. So some of these big numbers are being cracked in the global average of these greenhouse gases. Going to the next slide, we can have a look at where the extra carbon dioxide is coming from in terms of carbon dioxide flux. And this is expressed in gigatons of carbon dioxide per year. And where something is coming out of somewhere else into the atmosphere, we call that a source. When it's going from the atmosphere into somewhere else, we call that one a sink. And here's a measure of the different sources and sinks of carbon dioxide through time since 1900. And we can see that the majority of the sources, that's the shapes or the colours above the zero line, the majority is from fossil fuels and industry, but there has been some contribution also from land use change. So we change the land, that changes the amount of carbon that the land holds or takes up. The ones below the line, or the sinks, where that takes things out of the atmosphere, we can see that our friend the ocean is absorbing over 30% of the extra carbon dioxide that was in the atmosphere, providing a sink. There's also some from the land as well. So land use change has created a source, but also the land acts as a sink for carbon dioxide, and that also reduces the concentration in the atmosphere. And the rest is expressed in that lower light blue one, which is just what remains in the atmosphere. So let's Carbon dioxide is absorbed into the ocean and land, or it remains in the atmosphere. If we didn't have our friends, the land and the ocean, absorbing some of that carbon dioxide, the concentration of carbon dioxide in the atmosphere would be over 550 parts per million rather than about 400 where it is now. These plots are produced by CSIRO in conjunction with researchers around the world under the Global Carbon Project, and there's a website there where you can explore the carbon budget back through time and in different regions of the world. Okay, going to the next slide. Looking at the oceans, as Lynette said earlier, air temperature over Australia has risen by just over 1 degree since the reliable national records began in 1910. And for the oceans surrounding Australia, there's a similar amount of warming. They've warmed by about 1 degree since that same time frame of 1910. The top graph again is expressed as the difference between the anomaly from the 1961 to 1990 average value. So the values earlier in the century were typically below that average. The recent ones in recent years have typically been above that average value. And that change, that warming, hasn't been spatially uniform, hasn't been the same everywhere. And the bottom shows the recent trend in sea surface temperature just from 1950 to 2017, and with warmer or redder colours showing a faster rate of temperature increase, and the yellows showing a slightly slower rate of temperature increase, and nowhere around Australia has seen a decrease, or there's no blue colours. There's a real hot spot in the southeast of Australia. You can see there around the coast of Victoria and off Tasmania. And this is due to a strengthening of what we call the East Australia Current. So this is a current that brings warm water down the east coast of Australia down to the northern tip of Tasmania. And that has become stronger over recent years. So more warmer water is moving south in that current, creating that hot spot of faster increase in surface temperature. Okay, going to the next slide. A warmer ocean on average can lead to what we call ocean heat waves, or periods where the ocean surface is much warmer than average, just as it does in the air. Ocean heat waves can be much more persistent and last for longer than atmospheric heat waves because of the nature of water compared to air. And there's been some very notable marine heat waves in the Tasman Sea and off the coast of Tasmania and in a couple of recent years, including in 2015-16, there was a record-breaking heat wave, but also in 17-18, there was another heat wave there. But another incident where the temperature of the ocean was very much above average and had real impacts was in the Great Barrier Reef region. And here is a snapshot from the Reef Temp monitoring product at the Bureau of Meteorology website. And this is temperature described as degree heating days. So this is an integration of many days and how much it was above average for all those days, and then put on a scale of degrees days. And you can see that a lot of this area was in the very red colours with very high values of degree C days compared to average. And this was very closely linked to the extensive coral bleaching in 2017 that was seen on the Great Barrier Reef. And part of that back-to-back coral bleaching that was seen 2 years in a row. Okay, going to the next slide. This graph, I think, deserves to be just as well known and as iconic as any temperature graph, as a description of what's happening to our climate in recent decades. This is the change in the total ocean heat content of the oceans. So the ocean is absorbing over 90% of the extra energy from the enhanced greenhouse effect that we've created. So that means a lot of energy is going into the ocean and being stored in that water, and that has saved us from experiencing a more rapid rate of increase in temperature on land. So this goes back to 1960. You can see early in the record there was quite a lot of uncertainty about trends, but as time has gone on and as there's been improvements to measuring methods, and there's been the start of the very successful Argo program that Australia has been one of the leaders of, we can better measure and more accurately measure the amount of total energy in the oceans. So the scale there is in zetajoules, or 10 to the 22 joules. Just to put that in some kind of perspective, you might have eaten lunch today with a certain amount of kilojoules in it, the measure of energy, how much energy you get from in something. This rate or this amount of energy going into the ocean in just the last few years has been estimated at about equivalent to 3 nuclear blasts per second. That amount of energy going into the oceans and being stored as ocean heat. And you can see in the last few decades there has been a very steady increase. There's a lot less variability than there is in surface air temperature, even global average surface air temperature. There's ups and downs and wiggles in that rate, but this one is very steady, especially since the year 2000. Just seen a very strong increase and steady increase. Okay, going to the next slide. As oceans become warmer, and also as ice that was on land in glaciers and ice sheets melts and that water enters the ocean, we get a rise in sea level. So this is where the sea level rises on average. Of course, we get tides and things day to day, so there's a lot of variability in sea level. But this is the sea level once you remove all of those ups and downs and wiggles, and this is averaged over the world and this is measured using very accurate tide gauges and also satellite altimetry. That's measurements from satellite. And you can see this has been rising steadily in the last 100 or so years, since 1880. Again, the measurements have become more accurate as we've gone through time, so the uncertainty range has narrowed a little bit. And now we can compare two different independent sources of data, the satellites and the tide gauges. There's a fairly good agreement, and people are looking into why there is some difference there. But the overall trend is very clear, which is global sea level has risen by over 20 centimetres since 1880, and the rate has been accelerating in recent decades. You can see there's a slight kind of upward bend to that line, and the recent rate is something like 3 centimetres per decade. But of course, sea level rise is not experienced the same everywhere. So going to the next slide, we see there's been a different rate of rise here around Australia in the recent decades. This is the rate of change in 1993 through to 2017, expressed as centimetres per decade. And you can see that here the blue colours don't mean decrease, but they just mean a lower rate of rise. And you can see that in the southeast Australia, in that same area where I talked about the increased rate of warming due to the strengthening of the East Australia Current, in a similar area we see a higher rate of sea level rise off the coast, and also a hotspot in northern Australia. There are other factors that come into play to what we actually experience in terms of sea level change at the coast. So some places around Australia, the land is also moving, and some other places around Australia, there's other regional and very local factors that come into play to tell us what you actually experience at the coast. But this is a general picture of the rates of change over the last couple of decades off the coast. Going to the next slide. Another side effect of increasing greenhouse gases in the atmosphere is that it changes the chemistry of the air and also of the oceans. So CO2 in the air affects plant growth and other things, but then it also gets dissolved into the oceans, and this changes the chemistry and it decreases the pH, or an increase in acidity, in the ocean surface waters. Around Australia, there's been an estimated change in pH of over 0.1 units, and that may not sound very much, but remember that pH is on a log scale, so a change from 8.2 pH to 8.1 relates to about a 30% increase in acidity, or the availability of H+ ions to do chemical reactions. And if we see further increases from, say, 8.1 down to 7.9, this relates to a more than 150% increase in acidity and H+ ions. And this is having impacts and will be projected to continue having impacts and increased impacts if that increases on animals and other organisms that rely on calcium building to build their shells. These are things like corals, but also animals with shells. So this is kind of this other carbon dioxide problem, if you like. Okay, going to the next slide. So moving on to looking at future climate and estimating what the climate could look like in the coming decades for Australia and for the globe. Let's first look at the tools, some of the tools we use to estimate climate change and make projections of future climate states. On this graph, I've shown the observed temperature record in grey with a running mean put through. They're the black lines. And the grey window behind that is the simulations of the climate system done in Australia and around the world using climate models. And I haven't put an individual track of each one, but when you look at them in aggregate, you can see the range of variability and the change in trend through time. And the grey window does cover the black line. It does match that change. If we then run those same climate models, but without greenhouse gases or human changes, we arrive at the blue range of blue window, which doesn't include that upward trend. So this is one line of evidence that we use to do what we call attribution studies. This is to work out and disentangle the different drivers of change. And we just simply can't reproduce the recent warming using models, but also using our theories about without the increase in greenhouse gases. We can then use those same models, run out into the future under scenarios of different greenhouse gas concentration changes to make future projections of the climate. And you can see the start of those kind of projections that we produce on the right-hand side in the red window, if we were then to run those models forward. And that includes all of the different emission scenarios out to 2030. And you can see there's projected to be an ongoing upward trend in temperature. Of course, climate variability would come along on top of that rising trend, but we would expect the long-term trend to sit somewhere in that red window. Further out into the future, it of course depends on which emissions scenario we follow, whether we go to a low emission scenario or a high one, whether that rate will continue through the rest of the century at the same rate or plateau. And also marked on this graph are some dotted lines indicating roughly what the equivalent of a 2 degrees and a 1.5 degrees global warming above the pre-industrial level means for Australia. It's slightly more than the global average because land generally warms a bit more than oceans, and some areas like the Southern Ocean cool much less than the global average. Okay, so that's some of the tools that we use for looking at future climate. Going to the next slide. How have we done in the past in producing climate change projections and sending out messages about what we can expect? Well, there's been enough time now looking back to some of the earliest communication products and analysis about what we can expect about future climate going back to the early 1990s. There was some from the IPCC, the Intergovernmental Panel on Climate Change, all the way back to 1990. And here's a comparison for a statement put out by CSIRO in 1992. And on this black and white, no colour printed report, there was an estimated range of projected change in Australian temperature going out to 2030. And I've just marked that in red. And we can now see how we are tracking against that range of change. And you can see the observations have been tracking within that range, especially that ongoing trend. The thicker black line is definitely within that red window. and certainly above the null hypothesis, or the kind of default of no change marked there as a dotted line. So for the time, we would consider that to be a reliable source of information so far. I mean, we're not at 2030 yet, but it seems like it was not a unreliable kind of estimate of what we could expect. I mean, it was quite broad. We didn't want to, that statement shied away from being too kind of confident or narrow in their projections, but what they did produce seems to be reliable. Okay, so now going to the next slide. A changing climate, as Lynette kind of went through, doesn't just mean warmer temperatures or an increase in the mean annual temperature of Australia or in the world. It has other effects, and this is a summary of some of the other effects that we expect ongoing into the future, and with more under a high emission scenario and those effects slightly less under a low emission scenario. So temperatures to rise, sea level to continue rising, oceans around Australia to continue warm, and acidification to continue. More hot days and fewer cool days. Tropical cyclones, there's ongoing research in this area, and it's still an open question, but the current thinking is that we expect a decrease in the total number, but an increase in the number of very extreme tropical cyclones, but with a lot of year-to-year and decade-to-decade variability along the way. Extreme rainfalls, especially at daily and sub-daily lengths, to become more intense, leading to more flash floods. That harsher fire weather is projected to continue for southern and eastern Australia, and decreases in winter and spring rainfall for southern Australia, and an increase in time spent in drought, but again with that ongoing high variability. So that wraps up my sections of the webinar, and so I'll hand back to Lynette.
Or Angela. And yeah, I'll pass over to Ange to go through everyone's questions.
Absolutely. Thank you to everyone who has sent questions through. I will apologise now, as we have been inundated, and sadly we're not going to have time to take everybody's questions, but we will also provide you with an email address where you can send through any burning questions, and we'll happily address those at a later time. So our first question today is from Clara. Clara's asking, what were the atmospheric concentrations in the 1970s? Was it a tipping point? Michael, perhaps you can take that one.
So concentrations of carbon dioxide have been steadily increasing and kind of accelerating over the last kind of, time since the Industrial Revolution in about 1750. The 1970s was a period of kind of ongoing increase. Reliable measurements at Cape Grim started in 1975, so we've got some better quality measurements since then, but yeah, it was a period of increasing of carbon dioxide and others.
Thank you for that, Michael. Another question here from Liz. Liz is asking, what is the nationally average temperature for the baseline period? I understand it's in the vicinity of about 23 degrees Celsius. Please confirm, Lynette, perhaps, if you wouldn't mind.
Actually, just
Michael. Michael.
It's,
I know Michael did that on the graph.
21.8.
Wonderful. Thank you, Liz, for that question. Another question here from Peter. Is the observed rainfall decline in the southeast expected to continue as a trend? Lynette?
So I'll start with that, and then I'll hand over to Michael, because I know he's done work on the projections. So it is. So some of these trends that we're seeing are trends that are projected for the future as well. And the rainfall decline across southern Australia is projected to continue, especially across that winter-spring period, and southwest Australia as well. So rainfall's are a lot more variable than temperature, but I'll say those rainfall projections for southwest Australia is one of the most confident rainfall projections that we see around the globe, and we're seeing those trends there. And it really has been projected over a number of years and iterations of models as well. So I'll pass over to Michael.
I'll just back you up on that, Lynette. The southwest Western Australia decline has got a clear signal of climate change already there, and is projected to continue. That's globally a very kind of notable case. Southeast Australia is a bit more of an open question of how much is due to human influence already, but the projections are fairly certain or fairly confident about an increase in the long-term trend in Southeast Australia in winter rainfall. But of course, we've got to frame this in terms of very large ongoing natural variability. So it doesn't mean every year gets drier than the last, or every year is now a permanent drought. There's obviously a lot of variability in Australian rainfall.
I'll just jump in there too, Michael, because I think that's a really important point that you just made. So we talked in our talk about the trends and the variability happening on top of that. So it's not going to be every year is not going to be the hottest year on record. We're still going to have those warm years, cool years, wet years, dry years, but they're happening on top of those trends now, which are changing the frequency of dry years or the frequency of those warmer years that we're seeing.
Thank you both for that. And we've received a question from Colin also. This is regarding oceans. There seems to be data missing from for Bass Strait. What was the outlook for Melbourne? Michael?
Is this in terms of sea level?
I think it could be, because it didn't map it closer to the coast.
Yeah, we deliberately didn't map it close to the coast because those local factors can really actually affect that. So, for example, the area of more rapid increase in Southeast Australia is seen off the coast, but some of those local factors means that some of those towns on the coast haven't seen that reflected in their tide gauge changes. So there's other information about sea level out there, and I encourage you to go and look at things like Canute or Coast Adapt. I can send you these links to get the changes right at the coast. But yeah, we deliberately left a gap between what these satellite data can tell us and what people have actually experienced at tide gauges on the coast. And that's through to various factors about what happens right at the local area.
And I'll just jump in there too, so Michael raised the point that there's a lot of research out there. So the State of the Climate, of course, summarises a lot of the research that is out there, and we do have an extensive reference document available with the report if you're interested in following it up further.
Wonderful. Thank you for that. Another question here from Clara. Clara's asking, acidification is extensively researched for oceans, but what about freshwater ecosystems? Michael, would you like to take that one?
I'm not a subject matter expert in this area at all, so I wouldn't be confident to give you a full answer. I'm not aware of the research at all. I don't know whether it's just a saltwater problem or if it's freshwater as well. That might be something we'll have to get back to you on.
Oh, yeah, absolutely. Clara, please send us an email. I'll read out the email address a little bit later in the presentation so we can have a chat about that one. A question here from Ming. Ming is asking, how is acidity measured in oceans?
So that plot showed the pH of oceans around Australia. That relies on measurements, but then those measurements are put together with a model to estimate, to fill in gaps and to fill in gaps in time and in space. So the chemistry of the ocean is fairly well understood about what different cycles occur and what determines the pH, and the plot is based on things that are measured but then put together in a model to get a more complete picture.
Thank you, and thank you, Ming, for that question. Question here from Hamdan. Is it always ocean and atmospheric activities, or are there other indicators of climate change? Michael, would you like to take that, or Lynette? Or
I'm happy for Michael to take it.
Yep.
Yep.
Sure.
Yes, there are.
So I think it's really important to realise that there's various and fairly independent lines of evidence that the climate is changing. So there's measurements at weather stations of the temperature, but there's also measurements in the ocean of temperature and heat content. There's measurements of things like glacier and ice sheet changes. The majority of those are losing mass and are becoming smaller, indicating that temperature is rising. And there's also other measurements of air temperature at different levels in the atmosphere. So it really is many different lines of evidence in different domains put together that gives us a picture of a warming climate system. Yeah, not just the surface in the air temperature, but oceans, ice, land and air.
I'll also add in too, we haven't measured it in the report, but it's also reflected in a number of in natural systems that are responding to all these changes. It might be changes in migration, changes in vegetation that we're seeing, seasonal changes in, flowering times or such. So there's a number of lines of evidence.
Thank you for that. We have time for one more question, and we'll take this one from Peter. Thank you, Peter. What sort of projection is there for groundwater storage in the future? It rarely seems to be mentioned. Lynn, any thoughts?
We haven't gone so far as to look at groundwater storage, and honestly, this is something I was thinking maybe future State of the Climates would like to look at. So I can't give any confident projections on that at this stage, but I will say that we have looked at, we do have groundwater. We measure groundwater as part of at the Bureau, and so in recent years we've been able to start to get that national picture of how groundwater is changing and the groundwater reserves that we have. So yeah, I think that's an important point as well. It's really, it really comes back to this underlying data. You really need to have the data there that you can examine to get these pictures. So this is definitely something that we would like to look into further.
Wonderful, thank you.
Sorry,
Michael, was there something?
I was just going to add in a little quick one. Just on top of that is, so projections of rainfall, evaporation and water balance are an ongoing research area in CSIRO and the Bureau and elsewhere. To take it through to water availability and impacts on water availability and water storages and so on, you needed to take it to that next step of not just considering changes to rainfall and evaporation, but also what people do. So if we use a lot more and we draw a lot more or less, and the population demands more and the industry demands more, that's also a big part of what water availability is like in future.
Yeah, it's a good point.
Perfect. All right, well, we've reached that time where, Lynette, if you wouldn't mind flicking to the next slide, we'll make our closing remarks. So for further information, please take the time to read the report or watch the accompanying videos. We have an extensive reference document that accompanies the state of the climate, and it's available from our website. If you would like to continue the conversation, please use the hashtag BOM webinars in your LinkedIn posts. We'll be delighted to hear from you. And if there is something in particular you'd like to discuss further, or if we've missed your question today, please email us at helpdesk.climate@bom.gov.au. Next slide, please. Our next BOM webinar will be our autumn climate and water update on Thursday the 7th of March, so don't forget to register. And that brings us to the end of our webinar today. A big thank you to Michael and Lynette for your time and sharing your knowledge, and to our audience, thank you for tuning in and joining us today. We hope you enjoyed the session, and we do hope you'll join us again next time. As mentioned earlier, this session has been recorded, and we will have the video ready for your on-demand viewing pleasure within the next week, so please watch this space. Finally, but most importantly, we want your feedback. It's our aim to bring you the highest possible quality webinars, but we can't do that unless you share your experiences with us. Once we close this webinar, a short survey will pop up on your screen, and we'd be very grateful if you could complete that anonymously for us. Once again, thank you for your time, and we look forward to seeing you again soon. Goodbye.